All right, yes. My name is Jason. I will be the MC for the show. Thank you so much for coming. Right now, we're going to have a very special event. It is a fireside chat. It is a discussion with HPC Visionaries. These are the luminaries. These are the people who have their finger on the pulse of everything HPC, and it's going to be a really fascinating conversation. I want to give a brief introduction because they know everything. I'm going to let them talk, but I want to give a brief introduction to everybody, and I want you to give everyone a round of applause after I announce everybody. We're going to start off with, from the Argonne National Laboratory, we have Rick Stevens. Joining us from the Leibniz Supercomputing Center, we have Dieter Kranzelmüller. From the University of Cambridge, we have Paul Kalea. And from Los Alamos National Laboratory, we have Jim Lujan. And of course, acting as our host for this fireside chat is Intel Corporation's very own Deepak.
Thank you, Jason. All right. Good evening, everybody. Can you hear me back there? Awesome. Thank you. Welcome, and thank you for making time for our fireside chat with no fire. We don't want to violate any codes. Imagine there's fire here, and we're sitting around the fire. It's great to be here, and I'm privileged to be amongst these amazing luminaries from the world of HPC. Let me start by congratulating our OEM partners, Dell, Lenovo, HPE, as well as these amazing HPC supercomputing centers, the Argonne National Lab, the Los Alamos National Laboratory, University of Cambridge, as well as LRZ, for making it into the top 500. And kudos to all the teams that have worked tirelessly for I don't know for how long to make it to this amazing milestone. We are all very happy, privileged, and proud to be here. Yes, thank you. Yes, thank you. We all appreciate you all making time for this fireside chat as well. We're going to have a wonderful conversation about the world of HPC, both the opportunities as well as challenges around standing up massive scale HPC systems. Without further ado, let's dive in. I would love for our distinguished guests to introduce themselves, tell a bit about yourself, tell a bit about the systems you're building, as well as the problems you're trying to solve. Rick, let's start with you.
Okay, well, thanks, Deepak, for that. So I'm the Associate Lab Director at Argonne National Lab for Computing, Environment, Life Sciences. I'm also a professor at the University of Chicago. And what really motivates me for all the work, and not just me, but really leading the team and building the relationships, particularly with Intel and with HPE for standing up Aurora, is that we're trying to do something that is very hard, but if you accomplish it, can do a lot of good. I mean, really great good, right? In terms of making progress on problems like understanding global warming and how to adapt to that, or fundamental questions about the universe, like what's dark matter, and really making headway around how are we going to couple high-performance computing and modeling and simulation with huge advances in AI. And fortunately, we're building these machines out of technology that's equally good for doing simulations and for training the world's largest and most powerful AI models. And what we're trying to do at Argonne and with all of our collaborators and partners is to bring those energies and those activities together to create a new way of doing science that couples simulation and couples advanced AI models that can be used for scientific discovery and for understanding and mining scientific information. We've been doing this for, of course, many years, and this is just the latest of a series of machines that we've created. And it's not the last of these machines, right? There will be more machines. But what's really different right now is the convergence between simulation, AI, large-scale data, and the fact that there's so much new energy in the community around how to build very large-scale language models that can be applied to problems like improving the software that could be used to advance simulation in some problem and closing the loop on that. And that's what we're going to do with these powerful machines over the next couple of years. And it's just so great to have a partner like Intel, who we've been working with for many years. And it hasn't always been smooth, and we're still only halfway to standing up Aurora. But it's going to be awesome when we get to the end of it. And we're just so happy to be here and to let everybody know that we're making amazing progress. So
thank you. Thank you. And when you're building one of the world's largest supercomputers, there are bound to be some hiccups, and we could not have asked for a better partner and a more stable hand with the kind of vision you have. So we are privileged to be working with you, Rick. Dieter?
Yeah, my name is Dieter. I'm the chairman of the board of the Leibniz Supercomputing Center, which is one of the national centers in Germany. We are here from Bavaria. You can also see that at our booth later. And our goal is, well, not so much different from what Rick said, but maybe I'll explain some specialities. Yeah? The goal we have is to support the broad field of science, everything from astrophysics to you name it. And we really want to have something where they can use these machines that we're building as a tool for their daily work. So the machines should be easy to use, so to say. We have users which start, we call them the clickers. They just use the systems by clicking buttons, but also those, I'd say, physics people on the other side who want to really know about every bit that's going on in the system. And you combine these two dimensions of diversity, so from the usage pattern to the different fields, you need a system that is really able to support each of these activities. And that's what we have with SuperMOOC NG. This is really a system that is wonderfully stable, that is really kind of delivering science every time, every day, and that's really giving the users what they want. And with the latest extension of SuperMOOC NG, we're doing what Rick said. We are adding AI as an additional tool, so it can also incorporate anything we have with AI into the science field, and it accelerates our time to science, our time to scientific discovery.
Wonderful. Machines should be easy to use. That's awesome. Paul?
Yeah, so we're one of the UK's national HPC centres. We've been operating now for around 16 years. Traditionally, obviously, large x86 platforms, again, easy to use because we have a wide diversity of users, exactly the same as yourself, across all disciplines, engineering, medical, clinical, science. So, again, now the UK has started to up its investment. So the UK has been lacking in investment for HPC for some time. It's now signposted much larger investments and a focus on AI. So working with Bristol University, we're part of the UK's AI research resource, which is two large systems, one in Bristol, one in Cambridge. Cambridge is the first one. It's a large Ponte Vecchio system. And again, we're looking to how we marry simulation with AI and get those things working. And the one feature that we've been developing for the last 5 years is an OpenStack cloud implementation on top of it, again, to give flexibility and agility and give our users the resources as they need them.
Amazing. And one of the things, Paul, that I have been impressed with in our engagement is the speed of execution and the rate at which you have moved forward. It's infectious and impressive.
I mean, it's 7 months. So we had the idea for this system 7 months ago. It took 5 months to arrange the funding, 8 weeks to get the hardware, and 3 weeks to build it. So it was pretty fast.
That's awesome. Yeah, it's amazing. Jim?
Oh, thank you, Deepak. So I'm Jim Lujan. I'm the program director for high performance computing at Los Alamos. My role is to help usher in HPC systems into the NNSA Los Alamos laboratory. Crossroads is the most recent one that we have with an NNSA. And again, like Rick, we've been partnering with Intel for quite some time with our previous system, Trinity. And so we're very excited to start seeing that technology start to support the national security mission for the Department of Energy. We're really pleased with essentially the ease with which we're able to take our existing modeling and simulation capability, migrate it onto the newer technology, and see an amazing, performance improvement just by essentially upgrading to the latest Xeon Max technology. So we're very excited. We're eager to see the next phase of that as it starts going into production. And the work that we do will eventually trickle down into a variety of different sciences and not just focus specifically on the national security mission. So again, we're really pleased that we've been partnering with Intel for quite a long time.
We are incredibly privileged to actually be partnering with you on such an important mission and initiative. Thank you for the opportunity. Mm-hmm. I'm going to ask each of these amazing visionaries a question about their vision, their work, their view of the future. So let's dive in. Let me start with you, Dieter. What vision do you have for the systems that you're building beyond what you shared with respect to the breadth of the research as well as the simplicity of use? Share a bit more about your vision.
Well, the goal is basically to anticipate what the scientists' needs are in the next couple of years coming up. So while these systems are running, we are kind of constantly updating the environment for the scientists, and they can use the combination of these powerful processors, whatever is a storage network, in order to fulfill their particular goals. And I was expressing already ease of use is one of these things, yeah? I mean, I have a wonderful example here. I had this one person which I met accidentally. We came to talk, and he has never used an HPC system before. And the important thing he does regional effects of the climate change. Yeah? And that is very interesting. And he didn't have the idea of using this system. We got him up from 0 to one of the top 20 users on our system, spending 120 million core hours on developing these visions. And you can read about that. That's in the current IPCC reports, because it explains what we have been doing on this system. And there's AI already in there, because he also wants to understand how this affects the data that he has been producing, how it kind of refers to extreme weather situations like flooding, like droughts, and all that shows how it fits together. We got him from 0 to 100 in very short time.
Amazing, amazing. My next question is for you, Rick. One of the most defining characteristics of the world of AI is the speed with which things are evolving. How does the speed of AI evolution impacting and influencing your vision for future of computing?
Well, it's a really good question, because every day we think about, first of all, how far we've gone. I mean, not just Argonne order, but the whole community in terms of where AI is at now, right? When we first started thinking about exascale back in 2007, AI was not on anybody's agenda. Climate was, energy was, right? Data was a little bit. And now it's what everybody's talking about. It's kind of infused into everything. But it's moving so quickly from both an understanding of what large-scale AI models are going to be capable of doing, but also how to build them and how to build them better, or how to build better models. And it's very likely that sometime in the next few years, we don't know when, that we will have some better algorithms, some better ways of building these models. And it will be super important that we have general purpose high performance computing hardware in our centers, because a new algorithm could come out tomorrow that maybe is better than Transformer, or better than what we have for Stable Diffusion or something like that for generative models. And by having a general purpose architecture, we can implement very quickly those new ideas and test them at scale. So that's a principle, I think, that's very important, and kind of underpins the whole conference, right? That there's always been trade-offs between custom hardware around one problem that can solve that problem amazingly well, and progress on general purpose hardware that gives you the flexibility to imagine the future and then implement it. And I think AI is, because it's moving so quickly, we have to err on that general purpose direction in order to not box ourselves in, and to be able to respond quickly if something, a new opportunity arises. And I think the kinds of hardware that we're building with Intel and the future systems that we can imagine with Intel are going to be directly in that space. And so I think that's where it's going, and it's just going to be ever more exciting. And in the next 5 years, it's just going to be mind blowing, I think.
It is. It is. Actually, in last 5 years, the parameter size in large language models has increased by 15,000 times.
Yeah.
I mean, ChatGPT, which has been one of the catalysts for mainstreaming AI, was fewer than a couple 100 billion parameters, and we're already talking about trillion parameter models within a year of ChatGPT coming out. It's truly mind-blowing. My next question is for you, Paul. How has Intel technology helped you stand up your systems, and what is your vision for the real-life science problems that you intend to solve?
Yeah, so with Intel, we've been working in a co-design partnership along with Dell for a long time. So Dawn, although it was quick to implement, the co-design partnership behind it was 2 years in the making with the application community. In particular, one of our strong stakeholders is UK AEA. These are the UK's fusion development community. So working closely with science domain and our technology partners, we can design these systems. And that co-design relationship is vital. In the future, again, we see real heterogeneity. So general purpose GPUs. Obviously, the Xeon range is still the workhorse for probably 99% of my users by user base is Xeon. Like some of the large consumers have obviously ported to GPU, but Xeon is still the workhorse. So we see much more heterogeneity, Xeon, GPU, and then more specialist architectures like Gaudi. So we'll be designing for this heterogeneity. And I think here the programming environment is kind of key. One of the main detractors to Intel is one API. And that freedom across architectures, I think, is key to lower that programming barrier. Otherwise, you get stuck on the programming. And then we look to where we push this. And I think one of the main domains that we're going to push into is clinical medicine and how we can get these capabilities used by clinicians in the clinic. And again, their ease of use along with data security, those two things are a bit of an oxymoron, but if you can make it easy to use and secure, these technologies can really be deployed in the clinic, not just in the research lab, but in the clinic. And that's one of our major areas of advancement, is pushing this into the clinic.
Wonderful, wonderful. Jim, Paul talked about the developer community that his team's working with. We at Intel strongly believe that the software developer as a persona is going to be probably the biggest contributor to evolution of HPC and AI computing of the future. Tell us a bit about your view on the role the developer community will play, as well as the role the programmers will have in evolving HPC in future.
Well, absolutely. Although we're a little bit uniquely focused from the perspective of the mission that we have to try and accomplish. Clearly what we're seeing from the developer community within our organizations is trying to see where we can optimize and enable more of that efficiency on the processor that we have, right? And HBM, as part of the Sapphire Rapids, is clearly enabling that. So where the developers are pushing is how can we gain better use of the processors that we have. And ultimately what it is that we talk about is improving that time to insight. Yep. So in getting that improved time to insight and then combining that with AI, in helping to steer some of our mod sim, we hope to be able to get to better answers more quickly than we ever have before. So the developers are clearly pushing in ways that we, are driving more of the processor efficiency and design from our perspective. I think, and then there's this whole new area of how we're going to be applying what we've learned from an AI perspective. So I think there's still some unknowns in that aspect, but clearly, how do we gain more efficiency? How do we get that better time to solution moving forward? And so it's going to be a bit unclear, at least in our perspective of where that's headed.
Got it. Very helpful. Now, while all four of you work in different places and solving different complex problems, I think one of the things that kind of binds four of you and makes you so successful is your ability to peek into the future, imagine the future, and then make it happen. This is one of the most preeminent gatherings of HPC enthusiasts on the planet. So my question, the same question to all four of you. We'll start with you, Dieter. We'll then go to Paul and then Jim, and we'll bring it home with Rick. Tell us about your vision for HPC computing over the next 5 to 10 years, or as far into the future as you want to peek.
Well, the vision for HPC is to give us those solutions to scientific problems that help society, that help us on our everyday life.
Yep.
And I think we're getting better every day as our hardware is getting better and our software is getting better. And I think that's a goal that's worth for investing all our energy.
Great. Paul?
Yeah, I think the vision for HPC really has to be the vision for AI, because obviously the market size of AI is going to dwarf HPC. There is no HPC, there's AI. And if you want to get advancement in HPC, you better start thinking how it can use lower precision. You better start thinking how it can use AI hardware.
Absolutely.
That's where you're going to get great gains in HPC. Not HPC, the HPC market is going to have to follow the AI market, and that's going to have to be the vision. It's going to be tough. We're going to have to go away from double precision for everything.
Yep.
It's going to be a different journey from what we're used to. That's the vision.
100%. Yes.
Yeah. And then from my perspective, you know, clearly where I think HPC is going to be heading is where clearly we've been focused a lot on the technology from the perspective of what can the processors provide in order to help us achieve basically understanding scientific models. And now what can we do to then apply those models? Where I think we're headed is basically an abstraction of being able to, instead of being so hardware focused, the hardware is basically just going to be a capability that's nobody's going to think about that. It's all going to be focused on how can AI and how can the mod sim work together to be able to start looking at solutions. And so, again, I think as we move forward, the hardware and the performance efficiencies that we're getting out of it are basically going to just not be at the forefront anymore. We're going to focus solely on what that capability can provide from a software and scientific solution perspective.
Great. Rick?
Well, I'm trying to think about how to be more crazy than what you guys are saying, right? So, I mean, clearly AI is going to be the most important thing. It may be the last most important thing that we do, in the sense that if we can build powerful enough AI systems, they will help us figuring out what next hardware systems will look like. They will help us write software. They will help us in working out the connections between domains and connections between underlying mathematical models and logic models and so on. And the question is, how do we do that with minimal friction, but also build AIs that will be safe and reliable and trustworthy by the millions and billions of people that will be using them, but with a particular focus on what does AI and science really need to look like, and where, you know, not all of HPC is used for scientific problems, but probably everything that we've historically used HPC for will be touched in some way by advanced AI systems. And there'll probably be some kind of grand unification in some sense. We won't have millions of models. We will have handfuls of incredibly powerful models that will be able to do many things for many people. And that transition from where we are now in HPC infrastructure and architectures to the future infrastructure needed to support that kind of a world is what I think we have to work on. And it could happen very fast. I mean, it could happen clearly in the next decade. And maybe the sooner it happens, the better, in the sense that it will be so capable and enable us to make so much progress on so many problems that affect society and healthcare and fundamental understanding of the universe that we need it, and we need it soon, given how many problems we're facing in our modern lives. So,
agreed. And we, you know, at Intel, believe that the AI transformation we are in the middle of is going to be as big a generational transformation as when the PCs showed up, or when the internet showed up, or when the smartphones showed up, or when the cloud showed up, if not bigger. We just feel that we're privileged to be in the middle of this transformation. Well, for the last half an hour, I was privileged to be in the company of these amazing gentlemen. Thank you for making time. I hope you get to spend more time in our Intel booth. You will see live code demos, talks, code workshops, So enjoy your time here with us and our supercomputing. And again, thank you very much for making time. And thank you all
Thank you,
for
Deepak.
making time.